This is the alternative meeting on the Lorentz transform, and our first speaker will be Nick Percival. Go ahead, Nick.
I'm going to discuss the Lorentz transformations. The first point is extremely important. There are two very different versions of the Lorentz transformation equations. They look mathematically identical, which adds to the confusion, but Lorentz's original transformations were based on a model where there is a single preferred frame, and its velocity, its absolute velocity with respect to that single preferred frame. It's in the transformation equations. Then Einstein came along, and basically he created a polar opposite of the Lorentz model. He said that all frames are equal. Thus, he had an infinite number of observer-centric models, all of which disagreed and presented different physical models. In fact, in Einstein's version, each observer thinks that he's in the single preferred frame. So that's an invalid assumption and should cast some aspersions on to the validity of Einstein's model and Einstein's version of the Lorentz transformations. I go into this in much greater detail in another video, video 29B in the Nick of Time series. Okay, we'll take a quick look at the meaning of the Lorentz transformations. The unprimed frame is the preferred frame, or the so-called stationary frame, and the primed frame is the moving frame. So when you go from the preferred frame to the moving frame, you have to adjust. For the X adjustment, X is the location in the unprimed frame, and really two adjustments there. VT represents the distance that anything that is at rest in the moving frame has moved in the X frame. So that movement has to be taken out. And the 1 over the square root term is simply the Lorentz factor, and in this case represents length contraction for both special relativity and Lorentz's theory. They have different physical meanings, though. Similarly, for time, the Lorentz contraction factor comes from time dilation, or in Lorentz's original equation, it was called clock retardation, talking about a physical effect. Now, the Vx divided by c squared term comes from how you do clock synchronization in the primed frame, in the moving frame. There, one is assuming that in the Lorentz's original transformation, one is assuming that the moving observer will incorrectly assume that the speed of light is c in all directions in his frame. But that's not true. because the speed of light will depend on his motion with respect to the preferred frame, in Lorentz's case, the ether frame. So V divided by C shows how big the correction factor is. Let's say V is 1/10 the speed of light, then the correction factor will be 1/10. And X over C, the farther the clock you're synchronizing from using the origin standard clock, the farther away you are, the larger that correction factor is, because it takes longer for the light to get there. So the fact that you're using an incorrect speed of light, the total cumulative error depends on how far away the clock is and how long it takes for light to get there. And X divided by C shows the magnitude of that error times the error effect, V divided by C. And the C in the numerator in this case just transforms the units from distance to time. Now the Vx divided by C squared term doesn't make any physical sense in special relativity. It just carry over from Lorentz. Also, even in Lorentz theory, if the clocks are synchronized in the single preferred frame, all the clocks, both in the stationary and the moving frame, then that term is no longer needed. And in fact, for GPS, all the clocks are really synchronized together. The Earth-bound clocks and the satellite clocks are synchronized together, so you do not need that correction factor. As noted before, the base Lorentz transformations look mathematically identical for the Lorentzian ether model and for special relativity. However, their use and meaning is quite different. Regarding their physical meaning difference, for Lorentz, velocity is absolute velocity with respect to a single preferred frame, namely the ether frame. For special relativity, V is relative velocity between any pairs of inertial frames. So in special relativity, if the observer is in frame A, and he's trying to transfer to B, an inertial frame moving with respect to him, then he'd use this equation. Similarly, if the observer is in frame B and he thinks that frame A is moving, he uses this equation as well. While the base Lorentz equations that we just looked at look mathematically the same for both Lorentz theory and for special relativity, for the inverse of those equations, it's quite different. In the Lorentz, those inverse equations are true physical inverses, and they're only used to go from the moving frame to the preferred frame. That way they can see what's actually happening in the single physical model of Lorentz. Instead of multiplying by the Lorentz factor for both distances, the x factor, the x term and the t term, one divides by the Lorentz factor. Whereas for special relativity, they are inverse Lorentz transformations are just a mirror image of the base transformations. The only thing that changes are the minus signs are changed to a plus sign. Such an inverse is only consistent with both frames just observing the other frame, but there being no physical effects, no physical length contraction, and no physical time dilation. And finally, we'll look at the empirical data. All the empirical data is consistent with the original Lorentzian LTs. Now, some data is also consistent with special relativity's Lorentz transformations, but only if the Lorentzian preferred frame is used as the base frame for collecting data, and there's no data from the moving frame. For the first time, the data from GPS and the Hathaway Keating experiment get data both from the base frame and the moving frame, and that data is atrimetric and shows that there's a physical effect and not a symmetric effect as special relativity predicts. And therefore they show that special relativity and its version of the LTs is invalid. But the original Lorentz transformations remain supported.
All right, I'm good to go. Unfortunately, I don't have anything set up right now. All right, I think what we have at this point is what I think is an interesting situation. So Nick has talked about Lorentz. I'm going to talk a little bit about Lorentz. And what Nick has said is going to be a little bit different than what I'm going to talk about. I'm going to talk about where this Lorentz transformation, how it evolved. And what we're going to see, what I'm going to explain is that we start off with Lorentz working basically on from physical principles, where he's talking about, let me share my video here, where he's talking about an ether. Lorentz has an ether concept, which he considers to be basically a stagnant ether. So the universe has this stationary ether. And his theory is that it's composed of electrons. That's kind of interesting. And what he's trying to do is, if the Earth is moving through this, the ether, this substance that's stagnant, and that's the assumption they use, stationary. And so the Earth has to be moving through it. So there's these optical experiments that have to be explained. Now, what the first thing he does is he comes up with that, I can't find here. I think I'm sharing the wrong.
We see your picture on the.
You see me, but I think I've got the, I kind of got confused here because I got too many.
Okay, we got instant, page 34, instant just between the mirrors A and A prime.
Well, okay, well, we're kind of screwed up here. How do I want to stop share? That's what I want to do. Okay, so you just got me here in a bunch of pictures.
I mean, you can select which window you're sharing.
All right, well, I don't really, I really don't have a presentation. I just wanted to refer to this equation. Okay, the first thing that Lorentz did was he tried to adjust Maxwell's equations. Now, this goes back to what Ian was talking about, where he talked about Hertz. What Hertz did, where he used the full differential, okay? And so Lorentz is sort of adding to what Hertz did. He's trying to modify what Hertz did. And the first thing he did was he added to get the wave equations in the ether, okay, he had this Vx over c squared term added to the time, and that's called the local time. So we got this. So the first thing that happens is, if you go back to what Nick was showing originally, where he showed the full Lorentz transforms, Nick talked a lot about this Vx over c squared term, okay? And that term comes from one of the first things that Lorentz did in his early papers about 1890, was he added this, what's called the local time, to the wave equation. So he was able to, get his first approximation to the solution was by adding this Vx over c squared term. Now, it's kind of a surprise to me to find out that was one of the first things that Lorentz did, okay, because the Vx over c squared term kind of has become mysterious as a result of Einstein.
Yeah.
But this was one of the first, this was the first thing that Lorentz added to the Galilean transformations. Okay, that was his first thing. Then later, he got involved in trying to understand the Michelson-Morley experiment. And that's when the what's called the Lorentz factor got added in. Okay. And then there's a paper in 1904 where the Lorentz factor appears in the transformation. So if you go back to what Nick was showing, that of the Lorentz transformations, we start off with the Galilean transform, which is x prime equals x minus vt, and then the t on the bottom, the t prime equals t. That's the Galilean transform. Then Lorentz changed that to t prime equals t minus vx over c squared. Okay, and then the final change, so to recapitulate, what we have is that the first thing that Lorentz added was the Vx over c squared term, and that would be the time in the ether. Okay, so there's a time difference relative to the rest frame time, the time of the Earth. So what we see is that the equations in the ether, the curl equations, the electromagnetic equations in the ether, have to be translated to the equations on the Earth, which is it's moving relative to the ether. So his first correction is Vx over c squared term to create local time. And then the next thing that he does, and that's the final change, is to add in the Lorentz correction factor, the Lorentz factor.
A quick question. If the Earth is carrying the ether along with it, wouldn't that Vx divided by c squared then go to 0?
I suppose so. I'm just trying to point out that the point I'm making here is that Lorentz basically was trying to develop a physical model, and what he was doing was he was working with the wave equations of the electromagnetic waves that propagate through the ether, and how these related to the ether being at rest with the Earth moving through it. And I'm not really trying, I'm merely trying to describe the process.
Right.
Now, the point that I'm making here is that Einstein comes along and he's got a completely different idea. He's not really doing physics anymore. He's doing, I would call it more metaphysics, okay? What he does is he introduces this idea that we're going to change our whole perspective of what space and time is, okay? So he's not even, he doesn't have a connection to the physical world. He's not working from physical things. Einstein's theory isn't really a physical theory. It's a idealization. So what you have is this big change in emphasis from what Einstein's doing, from what, Lorentz's physicality to Einstein's ideas, which is more about, oh, we're going to make a metaphysical universe and we're going to start with philosophical assumptions. And his philosophical assumptions are the two postulates, which is the principle of relativity and the constancy of light speed. Okay. Now, the real point that I want to get at is, it turns out that when Einstein's universe and the way that Einstein is developing his relativity theory, he has to make these assumptions about what time is, and then he gets into this definition of simultaneity. Okay. And then you get into where he's doing the calculations. Although he said that the speed of light is constant, he's using v plus c and c minus v plus c plus and minus v in doing these calculations. And the reader is sort of confused. I never really understood what he's talking about. If c is constant, why are you adding and subtracting the velocity? Okay, what's that all about? What's he doing? And so that's one approach. And I call that the two-way derivation of the Lorentz transform. Then once he gets the answers, he goes through the process again and says, okay, we can substitute this into this one-way light sphere equation. You see, that's this equation here where you see x squared plus y squared plus z squared equals c squared t squared.
Yes.
Right? That's the light sphere in the rest frame, or the initial frame. And then you have this equation down here that's the light sphere in the moving frame. And he says they're equal. Okay. The problem is that when you move the c squared t squared over to the left-hand side, you get 0 on the right-hand side. And when you do the same with the other equation, you got 0. So what you have are equations where you're equating 0 equals to 0. You follow this?
Yes. Yeah.
That sort of a system of mathematics has infinite solutions. There's all kinds of possible solutions.
Oh.
Okay? Now, this is the point I'm getting at. There's no proof of uniqueness in Einstein's theory of relativity. There's no proof of uniqueness of the Lorentz transformation. You understand that? Okay, so this is a big problem. Okay, so now it turns out that there's all kind, when you get into Selleri, who says he's got a new transform called the Selleri transform. Okay. I know Nick's familiar with that. How many people are familiar with the Selleri transform?
I've heard about it from Ron Hatch's paper, A New Theory of Gravity.
Right. Now, what Selleri does is he comes up with a different transformation called the Selleri transformation, because it turns out there's a whole bunch of, when you start doing the mathematics, when you take this mathematical approach, which is based on Einstein, you can get all kinds of different transformations of space and time. And the Selleri transformation is one of them that we recently talked about, that Stephen Gift proposed. So not only do you have the Lorentz transformation, it turns out that's a special case in which the synchronization is said to be 1/2 of the delay time, the time going in the forward direction and the time going in the back direction. Okay. And if you say that's 1/2, you set the clocks equal to 1/2, then you get this Lorentz transformation. Well, it turns out to be a special case. So now there's all these other cases, there's all these other transformations other than the Lorentz transformation that you can come up with in physics. So do you understand that point?
The thing that's being made as a mistake, though, is that c squared t squared. is dependent on the X, Y, and Z coordinates. It's
Well, I don't know that that's necessarily a mistake, because Einstein doesn't really, all he does is he talks about C plus V and C minus V, where he's going in the two different directions. And that's up here, if you look on in his, and see, it's right here. See right here, he's got the C plus and the C minus V in this differential equation here. And so you look at that and you say, what's he doing here? What's this all about? If the speed of light's constant, then why am I adding and subtracting C plus V? Well, he's doing this so he can come up with what Lorentz came up with.
Yeah, right.
Okay, so
Yep.
he knows the answer that he's trying to get
Yes,
before he gets there.
I was going to mention that earlier.
And at this stage of the paper, he hasn't actually said there's complete reciprocity, that the speed of light is constant irrespective of the speed of the source or the speed of the observer. He comes to that later, towards the end of the paper.
Well, this is kind of what the issue is. I have to sort of say, when I read this paper, this part of it here doesn't make any sense at all. It never has made any sense. I don't understand any of it. Okay, and the problem is, in what he's saying, he's got these postulates. I got two postulates. If you go back here to the beginning, he talks about the two postulates. We don't necessarily go back to. We know what the postulates are: the principle of relativity and the constant of light speed. And then he says, well, they're not contradictory. And then he says, okay, I'm going to prove to you that I can develop this theory based on these two postulates. But I'm sorry to say, I don't see how this theory that he comes up with has anything to do with the two postulates. It kind of seems like he's just pulling this stuff out of thin air, claiming that his theory is based on the two postulates, but he's really basically knows the answer from Lorentz beforehand, and he's just kind of cooking up some excuses to get the answer that Lorentz got, okay, and make it sound like his two principles actually do produce the Lorentz transform. Okay.
Yeah, I think that's what, remember I mentioned the relativistic Doppler effect could be derived from the normal Doppler effect if you added in the relativistic law of addition. And that's also struck me, as he knew what answer he wanted to be consistent with, and he'd solved a mathematical problem to make that happen. That's how it appeared to me.
And then that's pretty much consistent throughout this paper. If you go down here and we continue on through where he talks about the physical meaning of the equations with respect to the moving rods and clocks. Okay, now what he does is, in this particular section here, he says, oh, and guess what? I get the Lorentz contraction effect. My theory gives the Lorentz contraction effect, which, Lorentz had already argued that Lorentz contraction effect explained the null result of the Michelson-Morley experiment. So basically what he's doing here is he's making his theory agree with Lorentz had already said, right? Okay, and then we get over here to the time part, and where it gets to the time equation, and he miraculously gets a time retardation effect that Lamore had got from his ether theory. Okay, so what he's done is he's sort of shown that I copied other people's results and I got the same results that they got, but I had a different way of getting these results. And so that proves my idea that space-time, my principle of the velocity of light is constant, and the relativity principle, and that shows, and unfortunately, basically a lot of people bought into this, okay? Anybody got any questions about this?
No, I like it.
Okay. So the real problem, okay, now then we get this other issue of Minkowski coming in with his different theory. Now Minkowski, if you go look at his paper, I think I have it on here somewhere, but anyway, Minkowski solves the problem of the two equations equating to zero by he puts a constant in there, okay? And so he sort of avoids the problem of 0 equals 0, all right? And now his theory is kind of interesting in that he says there's a 4-dimensional space-time. Okay, now here's a good question. Why is this? Why is this? Okay, what we had in the beginning, if we go back to these equations here, oh, where are they? You notice that we have x squared, y squared, z squared equals ct squared, right? So what we have is a 3-dimensional space, 3 dimensions in space, and a parameter in time, okay? Time, and so what you can do is by moving the equations over, taking time and shifting it from the right-hand side to the left-hand side, what they're doing is they're making time one of the independent variables in the system of equations. So instead of being a fixed parameter, which would basically normally be a constant, right? Now, by moving it over to the other side, it suddenly becomes a variable to be solved in the equation. Now, when we solve the equations, we get that time is changed from a fixed time. It's now a variable, and it's a function of velocity. So time is now a function of velocity, okay? It's no longer a fixed time variable of a physical process. So we started off with light being a physical process. It's progressing through space in this expanding sphere, right? And time is an independent parameter of this system of evolution, this evolutionary system that's changing in time, but not a function of time. Now this system is a function of time instead of being independent of time. And that's how you get to the 4-dimension space-time idea.
Yeah, can I comment on that?
Sure, go ahead.
Yeah, that's the rub, because time is not a dimension. It's not a spatial dimension. And I know I've seen these diagrams from Gross and Wheeler on gravitation and stuff like that, where they show some really cool relationships. If you kind of like move time in one axis and processes in the other axis, you come up with some really good relationships and visualizations. But that's kind of an error when you say that because it's the time itself is not a distance.
Well, it's basically because what I said was when you start off with this equation where x squared plus y squared plus z squared equals c squared t squared, okay, where c squared t squared is a constant on the right-hand side, okay, and time is a parameter of the evolutionary process, okay. So what they do is they move the time over to the left-hand side, and then you have this equation equal to 0. So x squared plus y squared plus z squared minus ct squared equals 0. And then you do that for the moving frame and for the rest frame. And then what you have is an equation where 0 equals 0. Okay. That, you know, every time I saw that, I just said, this doesn't make much sense. How are you solving an equation where you're saying 0 equals 0? Okay.
Or furthermore, if you use the parameter, say tau equals ICT, well, then you get x squared plus y squared plus z squared plus tau squared equals 0. Or x1, if you make x1 equal x x2 equals y, x3 equals z, x4 equals tau, you just get x1 squared plus x2 squared plus x3 squared plus x4 squared equals 0. So it looks nice, you know, it's sort of.
But what you've done is you've that's Minkowski's theory, which kind of
Yeah.
is okay. And so what happens is now you've introduced this time as an imaginary coordinate. Okay, because now you've converted everything into complex numbers. Now you have a four-dimensional space. Now you have complex numbers. Okay, so now you're not even dealing with physicality anymore. You're not in the physical world. You're in this metaphysical universe that's been created. And the real problem, sort of, in my view, is it's not a unique metaphysical universe. It's got all these different kinds of solutions that you can choose from. Okay, you've got all these different theories now. If you, as I was trying to point out with the Selleri theory, which turns out to be a particular case of all these different theories, depending upon how you choose your synchronization of time. Okay, in your development of your transformation equations, there's this parameter. And so what happens is they get all these different, you can get an infinite number of transformations, okay, of space and time. You don't just have the Lorentz transformation, you have all these other transformations of space and time that you can have. So the Lorentz transformation isn't unique. There's no proof of uniqueness of the Lorentz transformation. Okay, which in my mind is kind of a serious problem. Now you've also opened the door up to, okay, I can invent all these different kinds of transformations. And one of the Selleri transformation is kind of a nice one because people like that because it gets rid of the Vx over c squared term. Stephen Gift makes a big point out of that. And Roger, in his presentation to the physics conference, mentioned that because of that Vx over c squared term, you can't really reduce the Lorentz transformation to a Galilean transformation.
Right, but the way that Selleri did that was having an arbitrary standard of what is real time.
Well, the point is,
and real simultaneity.
Right.
So
The
when
point
you
is,
if
go
you
ahead.
synchronize all your clocks according to a single standard, that's going to disappear. That's what Selleri did.
Right. Okay. Well, my point is, yes, there's all these different transformations. There's a problem with the Selleri transformation because he has the Lorentz factor inverted for time. So that doesn't really agree with the distance factor. So the Lorentz factor for distance gives an increase in distance, or distance is dilated.
Yeah.
And then he's got time contracting, and that produces a contradiction, another type of contradiction. And so then that's not really very, the problem, what I'm really talking about here is what they've done is they've created such a universe, they've created all these metaphysical concepts that allow you to have an infinite number of possibilities in your space-time. In other words, space-time sounds good, but there's an infinite number of these space-time possibilities now. Okay. Yeah. But while they like to focus on just the Lorentz transform, that's only a special case of all of these possible space-times that could possibly exist. And so you don't really have a physical theory that's guided by physics.
Can I make a comment?
Sure.
Sure.
Okay, the minus CT squared, C squared, T squared, if it's physically related, it's related to a moving light signal from somewhere in some direction. It's not linearly independent of anything. It's dependent on where the source was, and according to Dowdye, what the velocity of the source was. But, you know, that's a different topic.
Well,
But
the
it's-
issue is that they make that go away by doing what's called evaluation. And you really don't, to a certain extent, you're really not concerned with that factor at all. Okay, what you're really concerned about is the rate of the clock. So in other words, by doing an evaluation, when Einstein does his calculation of time dilation, he makes the Vx over c squared term go away by setting at x equals 0. Okay, so you evaluate at x equals 0, and since Vx over c squared has x equals 0, it becomes 0.
So what you're saying is when the two frames are doing, doing this, it's only at one instant in time for all the future and all the past that his equations may be valid. But at the next increment of microseconds or nanoseconds or femtoseconds or Heisenberg,
You're overthinking it.
then it's not valid. The equation, then you have to invoke all these Lorentz transformations to make it look valid.
Well, this is all part of the overthinking that is involved in this because it's not a physical theory. Okay.
Oh, okay. So we need to move on and have a theory that's physically based that actually explains what we observed.
Well, that may be one way of putting it, I suppose. The real issue is that the real problem is once you've decided that you've got this principle of relativity and you want to put that in there, okay, then that allows these multiple frames. So the Lorentz transform was originally not a transformation between frames. It was merely a way of calculating for the Earth moving through the ether, a transformation of the fields that would appear on the Earth since the Earth is moving with respect to the ether. And it really didn't involve multiple frames. There was only one frame, the ether frame. Do you understand what I'm saying here?
Yes, I do, but I think it's a bit of a chicken and egg situation. I think historically, the Lorentz transformation was developed to invoke invariance between different frames, in electromagnetic theory. And then when they got sometime later to look at MMX, well, they found that if you adopted these equations, you get the result they expected. So it's a question of which came first.
Einstein sort of invented this whole idea of multiple frames, and I think that's really what needs to be clear. Okay, this is what happens when, according to Einstein, I've got two frames of reference. Okay, I've got one frame of reference S, that's where my pointer is, it's on the S frame. And then I've got this other frame of reference over here, S prime frame, that's moving. Okay, and they're moving relative to each other. See, he's got VT here. All right. And so what Einstein says is I have a sphere, physical sphere of light in the S frame, and I have another physical sphere of light in the S prime frame. Right? That's the Lorentz, what he says. That's what his theory says. Okay. Wilhelm, who wrote this particular paper, says this is absurd. Okay. How is this possible? This can't be. I can't have that. That's my physics. And then he says, okay, well, in theory of relativity, I can have an infinite, I can have as many of these light spheres as I want. See this picture where he shows all these different light spheres? He says, this doesn't make any sense. Does this make sense to anybody that I can have all these different light spheres, each one of them, sphere of light expanding in each one of these different frames that's moving relative to to everything else?
No, all those other frames presumably should have ellipsoids.
No, that's not what Einstein says. That's
I know.
Well, are they in the? We have to be confused, be be clear, if you have light emanating at one place like this and you're moving by, that's different than if you're stationary and the light's moving by, because you're in different locations at different times, depending on where you are in the sequence. The observer is in a negative position or a positive in the real world. So this is, I think this is bogus.
Well, this is what people say. Well, okay, well, I did a whole analysis on this, and my conclusion is that this can't be. The only time this can be true is when S and S prime are essentially at rest relative to each other. That's the only time that the two spheres can be the same for these two frames, is when they're not moving relative to each other.
Right. Okay.
So that says basically Einstein's theory is just nonsense, because it's not really based on physical reality. It's based on metaphysical ideology, because he's got this idea that I can make a metaphysical principle called the relativity principle, or the constant light constancy principle. Okay, light's constant has constant velocity for every inertial frame I can think of. You know, this doesn't make sense.
Well, Harry, there's another way to look at it, and that is whether Einstein agrees or not. He was influenced by the MMX result. And like Lorentz, they interpret it as, all right, observers will see the speed of light to be constant in all directions. And Lorentz tried to explain that in terms of the physical theory. But Einstein got rid of the basis of that theory, namely that everything is dependent upon having the ether frame as the base frame for calculating velocity, etc. So I think what Einstein was trying to do was say we have different observers, and the observers will observe the spheres to be
Well, you're trying to make
true
excuses
spheres
for him. That's not really what he says. What he says is physically, what his theory says is physically you have two spheres propagating from the origins of two relatively moving frames of reference.
Yes, that doesn't make sense.
And that just physically doesn't make sense. Now, the issue in my mind is physicists are believing in a theory that doesn't make sense physically. How's that possible? That's really what the problem is here.
Yeah.
Okay. And the people have been telling them for 100 years, this doesn't make sense. What you're claiming, you're basing physics on a metaphysical idea. Okay, and they say, well, but because, in mechanics, this principle of relativity works out really well, so therefore we think we ought to be able to apply it to electrodynamics. And, oh, yes, this theory is proven in all these experiments, and so therefore we're going to accept it. This, to me, is a philosophical fallacy of major proportions.
Yes.
But its utility is important too in engineering. And if SRT will allow you to compute things rapidly that otherwise would take months, if at all, then that has to be taken into account too.
Well, that brings up the issue that Nick brought up earlier, which is has to do with what the Lorentz ether theory, if you use it in one frame, you do get results consistent with experiment. Okay. So what their experiments are saying is, well, yeah, we've got two theories and the experiments agree with both theories, but we're only going to say one of them is correct.
Right.
But the real issue is, in my mind, is you have these philosophical principles. And so this has become a case where the philosophical ideology is sort of trumps physicality. I think that's really what the issue is here. The metaphysical mathematical ideology has trumped physicality. And
Amen
so-
to that. And it's even now, I think, gotten into politics. It's not only metaphysical, but it's an
Well, if you
interesting
can convince-
political
Right.
principle.
Well, yeah, essentially you're basically telling people, you know, that reality is what we say it is, not what you think it ought to be based on your perceptions of it.
Yeah.
So you know, that's the malleability of human thought is pretty evident there. Now, my theory is that the problem really is this idea of multiple inertial frames, and there really can only be one frame. You can have one frame, you can move the frame around, you can move its origin around, but this idea that you can have multiple frames all at once in which the velocity of light is c, even though they're moving relative to each other, just doesn't make sense. That's just not physics. That's not physical reality.
Right.
The c squared, in the terms I'm seeing, equation 1 and 2, c squared t squared, that's not independent. It's not a new dimension that somebody can just say, hey, there's a fourth dimension in some mathematical, you know, where you can have fifth, sixth, and infinite dimensions. That c squared t squared is tied to and dependent on where the source was, and as time evolves from that location, you know, the x, y, and z coordinates, it's not linearly independent.
Well, yeah, that's kind of the fallacy of that particular method. And really what happens is you get zero, you're solving a system of linear equations that equals zero. And, you know, that to me is problematic. I just can't imagine how mathematicians basically look at that and think that makes sense. But I suppose they figure out if you allow a fourth dimension, if you allow time to be the fourth dimension, now you have a system of equations, and you they sort of gotten away. Minkowski sort of helped him solve that, because you notice what I said was Minkowski assumed that it was a constant, not necessarily zero. Do you understand what I'm saying? He sort of fudged that problem away. Now, Slobodan sent out some papers that is kind of interesting. What I got out of reading these papers was these guys were using all this fancy dancy mathematics, and basically what they were saying was that Einstein's approach didn't make any sense because it was allowing too many frames of reference and they were contradicting each other. But as long as Minkowski's theory makes sense, because it's only got one four-dimensional space-time. Okay, so one four-dimensional space-time kind of makes sense because you've only got one space. There's only one version of it. You understand what I'm saying?
Yes.
So that didn't really, but the problem is you really can't convert Minkowski's four-dimensional space-time into three space without the contradictions that you get in relativity. So that basically has a problem as well.
Doesn't every observer have his own four-dimensional space-time?
Well, that, yeah, you might want to say that. You know, I thought it, you know, that occurred to me as well.
I'm going to discuss now time dilation, and I'm calling it a two-signal time delay theory. And I wanted to preface this. I was inspired more away from thinking that special relativity was the way to go by Dr. Henry Dowdye Jr., who has deceased, and his work has been taken offline. So as soon as I find out that his work is back online again, then, you know, I'll definitely let the group know. But if I misrepresent any of his work in any way, I just would like for people to point it out to me. That's all. Okay. So I don't mean to do anything that would misrepresent his work. And I'm learning. Thank you. If you appreciate y'all. So anyway, so I'm using the right triangle, and these are just spatial dimensions. And I picked the 3, 4, 5 because that's pretty easy to remember and look at and calculate things off of. And I'm saying that the speed of light is, near this value here, and these are fixed positions in space. And so I'm not quite sure I understand this moving reference frames and different those concepts the way y'all understand them. Like I said, I'm trying to learn things. The ether concepts strange to me also. But so basically, I'm just saying that I'm like, this is the frame that we're looking at, and we're going to do everything in reference to what's happening here. And so these are distances D, L, M, and 5C, 4C, 3C in meters. Now I do understand that in special relativity or gravitation, general relativity, you can do that kind of thing. If you just understand that we're not talking about a velocity, we're just saying that it takes light in 5 seconds, 1, 2, 3, 4, 5, light will travel this distance. And it's just a calculation. So there's no velocity involved here. These are just distances. Okay. And I'm just saying the observer is located at M in this discussion. So then what we're going to do is at time t equals 0, and I believe I'll just have a short comment on that. Time is now. So this is conceptual, theoretical. We're talking about events that may or may not happen, but we're in the now. So when I say time t equals 0, it's a process that leads, that we evolve through time now, where you have energy and mass and things with certain trajectories. And basically at time t equals 0, we have a flash of light here at the location P. And then in 1 second, it will have gone to this location here. Now, one thing I'd like to talk about on this circle, this could be a sphere, and I'm only showing things in 2 dimensions. And so at time t equals 1 second, the wave front, you could say, has gone to here, or basically I would, instead of a wave front, if it was like a burst of red light or something in all directions, we just saw a red light bulb, then what would happen is, this is a packet of photons moving in this direction. Okay, up here would be another set of photons moving up in this direction, but the general idea is it's easy to draw. There's less math if you just draw it as a sphere that's expanding. So in 2 seconds, it's here. 3 seconds, it's there. 4 seconds, it's there. And I said that wrong. 4 seconds, it's here. And then 5 seconds, the observer sees the signal. Now, let's just say there's no observation here too. I'm trying to stay away from any kind of quantum effects or anything. This is just a high level way of saying the light has actually reached this position. And then of course it continues on. And so this is just a condensed way. The figure on the right is a condensed way of showing all of those other slides in one picture. So you would say at SP at time t equals 0, this is signal P. And actually, if it was a capital S in my language, it would be the source. A capital S P would be right here. The source would be located right there. But small s sub p would, to me, is just a signal. Is emitted here. And in 1 second, it's here, 2, 3, 4, 5. And so at 5 seconds, this observer. Now I'm calling, okay, so now you'll notice I have up here delta t prime equals d divided by c in seconds. So you have 5 seconds. So you take the distance divided by the velocity of the speed of light over that distance for this physical phenomena of the signal traveling through space. That's basically the distance traveled is the radius of the signal, which would be velocity times time. So, okay, so in time, this is delta t. Now, when this signal has reached this position here, this down here is also delta t. In other words, if you look at it this way, the signal took so long to get from its source to this location. At that particular time, you could say we'll have another flash of light at this fixed position right here. So you have delta t in time across here and delta t time across here. We're not warping time or space or anything. What we're doing here is we're just saying that t equals 5 seconds to everybody. It is at 5 seconds. We are in the now of 5 seconds. A flash happens down here. Well, then it travels in 1 second, which would be actually 6 seconds. In the 6th second of our experiment, it has, this flash of light has traveled here in 7 seconds, and 8 seconds, in 9 seconds. Whoops, sorry. So in 9 seconds. So you see the sequence of events. So basically you had in 1 second signal here, 2, 3, 4, 5, 6, 7, 8, 9. And you'll notice that this delta time from this flash signal emission to the reception at M was 4 seconds. So that's why it's delta time instead of delta time prime. And then this is just a condensed way of looking at it. So, and you're familiar with it now. So at 9 seconds, the green signal, and it doesn't have to be a color green, it's just a way of visualizing 2 separate signals. So here's one diagram that kind of crams all the information into one perspective, one graphic. And so what you see is the flash signal, the source SP sends a signal SP that propagates like this in time. And at this time, you have at the same delta time of the travel of flight of this signal, we're going to emit another signal. Now, these are fixed positions, so there's no velocity involved in here except for of the signals themselves. So you can actually see delta time t here, 6, 7, 8, 9 seconds. So the observer at 5 seconds from his stopwatch, let's just say he has a clock and he notices his clock ticking at 5 seconds, he sees the first signal. He notices at 9 seconds, he sees the second signal. So from his perspective, I would just say the delay time between these 2 signals of emission from where his position is 4 seconds. Okay. And that's where this triangle comes in very handy, because you have the same delta time here on the hypotenuse as you do on the, let's say if this is the x-axis going horizontally. But you have a different time on the y-axis. And so now we can take advantage of that. So what you do is you just say, okay, if you use the Pythagoras theorem, that you could just say, well, let's see, what do we say? So d squared equals m squared plus l squared, backward there, l squared plus m squared. And so d is equal to c delta t, l over here is equal to c, well, delta t prime, I'm sorry, that was for d, and l is c delta t. And then m is a distance. There is a time delay, and I haven't been able to think through, like, say, control theory or whatever, because there really is no cause and effect here. It's just a time delay that was chosen to come up with this physical configuration. There's no cause and effect on, there's nothing that I'm saying here at all that coordinates the flashes at P and the signal at Q. It's just a time delay between the 2 signals. So then you wind up solving this equation. You get delta time prime is equal to the square root of delta time squared plus m squared divided by c squared. And really with this information here, that's really all you can conclude. That's all, I think that is all you can do here. However, there's a reason why I picked this configuration. If we're gonna look at another physical situation, we're using the same geometry. And what we're gonna do is we're gonna have a rocket moving at velocity v, and at time t equals 0 just happens to coincide with position p. And it's moving horizontally to position q with velocity v. So what we're going to do now is the rocket we're going to allow to arrive at at position q with the same velocity. There's no acceleration, constant velocity at time equals delta t prime. Okay. So that's what this diagram's saying. Then what we're going to, what I wanted to do was basically just say that this is two different things, because the previous example right here could be on, well, we said it's at time t equals 0. So if we're using a common system of time for everybody, then these two events basically are coincident. They're related in time, but they're physically separated, because in this event here, we just have a rocket ship that happens to coincide at the position, or you could say near the position where a lightning strike would happen at a fixed space or place in time, where a light would emit at P and a light signal would emit at Q. So basically you have this situation here that I described before. If you try to add the two together, you don't get M equaling V divided by, times delta T prime for a distance across here, and being able to use like some Pythagorean theorem, because there is not the velocity of the rocket itself may actually be related by the distance and the delta T prime, but it has no effect or cause on the lightning strikes. So you can't just say, well, let's use Pythagorean theorem here and do this solution. And that's what I'm coming up with next. So this is one phenomenon. And for the rocket, here's another phenomenon. You can say this. You can actually say for the rocket that it went a distance m in a delta T prime, and so with that velocity. But it's bad physics, or maybe I shouldn't use that term, but that's what I'm saying, for someone to start mixing these apples and oranges just because they happen at the same time. So if a person was to say, well, let's just take the m in this equation for the light signals, and let's plug in this velocity times delta t here to get this expression, then what we do is we go over here and we can say, well, here's this expression. Did I do that correctly? Where I just subtract this over here equals to this value right here. So I'm getting the delta time primes on one side. Then I'm dividing out the light squared on this side. And also there's a caution here. The caution I have, and it makes things more complicated, but we have to always be aware of this fact, that a velocity of something times the time equals the distance that something actually went. So it starts at one time and it moves a distance to at another time. It's somewhere else. Those two expressions, velocity times time, are coupled to that entity. And you can't just willy-nilly start saying, oh, c squared. We can just start dividing out here and making life look really simple and pretty. And you've destroyed the actual entities that are coupled to what I just described. So, but here I'm doing it for a reason. So we wind up with this expression here where we take the c squared, take it out here, and you can follow the math, and we wind up, oh, I'm missing a time right here. Oops, sorry. I was hiding the squares last night, so I can't do it in this mode, but there's a prime on this side. I can fix that on the final product. So this is actually the time dilation formula. And so what I think has happened is they're mixing apples and oranges or phenomena. Basically, the bottom line is this. I'm going back to here. This is a time delay between these two flashes of light. This is a velocity of an object moving through these positions. C times T in this direction is unrelated to the velocity of the rocket. If the rocket was going faster, it would actually be over here and the flash of light would have been here. If the rocket was going slower, the rocket would be here when the second flash happened over here. They're totally independent phenomena. So if you had a laser light, red light, actually pointed at the correct direction in going along this trajectory right here, it would reach here. It doesn't have to be an expanding circle or something, but it wouldn't matter how fast the rocket ship was, because the rocket ship is not emitting the light. The light's being emitted from a fixed position. And that's the big takeaway. You have C times T anywhere, and you have something associated with the velocity going in any direction. At that location, they're independent. They're totally independent. So then, this is what I discovered from Dr. Henry Dowdye. I went on ahead and took this and I documented it for purposes, because I believe this presentation may be on the internet. Now, I have not gotten permission to do this, but I know the source. I know his daughter, and she would probably give me permission, but I can't say that right now. So if this slides need to be, y'all can tell me how to go forward on that. But this is what he says, that the light signal, if you have a source moving horizontally at this position right here and emits, he calls it the burst signal right here. Then as you progress through time, the signal actually conserves momentum of energy principle, momentum and energy. Basically what happens is the signal evolves with a radius of CT, preserving the source center in free space. And so as the circle expands here in 1 second, expands here in 2 seconds, it expands here in 3 seconds. And voila, this observer sees the first signal in 3 seconds. Now this is my geometry here. It's not, I mean, this is his geometry, not the one from the previous example. So then he says this signal is extinguished, but another signal is emitted. It's the birth of a second signal. And so he calls this distance traveled tau naught. Now, as the source keeps moving, it emits a second signal while it's maintaining a constant velocity. When it gets here, the second signal has evolved to here. The third signal, I mean, the second signal in 2 seconds has evolved here, in 3 seconds has evolved here, and in 4 seconds, let's see, 1, 2, 3, 4, 5, 6 second time delay. This observer in this position sees the second signal. So therefore, what he's done is use the Pythagorean theorem to correctly come up with the special theory of relativity formula, but from using physics. That's what I believe. And so that was his purpose, was to show that there's a different way that actually light is being added to the velocity of the source. And that's why he shows the c minus v in this direction and the c plus v in that direction. So what I did was I said, let's go to the future. How about moving? This is actually, so then what happens is a burst signal happens at time t equals 0 here. It expands with the velocity of the speed of light in this, in the up and down direction, and in the forward and in the backward direction. However, the center of the signal remains with the source. So in 1 second, the source is here and the signal is here. In 2 seconds, the source is here, the signal is here. 3 seconds here, and you got it. So at 3 seconds, the observer sees the first signal. And then if you, then this is the death of the first signal, so we don't follow it out into the future. However, a second signal is emitted right here. And it propagates with the velocity of the speed of light around the source signal as it's traveling through space. And so at 9 seconds, this radius would actually reach the observer. So you have a time delay of 6 seconds. The two signals were emitted with a time delay of 3 seconds by the traveling source. The traveling source is already at the 9-second location by the time the observer has seen the second signal. So the time delay from the observer's perspective is 6 seconds, which looks like time dilation. However, if you use the Pythagorean theorem over here, which is tau prime squared, tau prime times v squared is this distance, is equal to, plus tau naught c in this direction, because remember the signal expands in away from the source at c, equals the sum of those two equals tau prime c, which is this right here. And that's where he comes up with this velocity vector addition. And so you'll have this signal length is actually coming back in this direction. And so if you take this formula and you reduce it, you'll get Einstein's theory of special relativity of time dilation with there's no ether here or anything as far as I know, because I just really don't understand the ether concept. But you see how time is related to all observers consistently in this model. So if you now go one step further, I made the comment to Henry, I said, look, the reason why you have this infinity here when 1 minus v squared over c squared is because the observer is perpendicular to the sending position of the source as it's moving horizontally on this track. And he said, that's correct. And then I go, if you move the observer inside, like for example, where you see this 3-second circle right here on the first signal, if the observer was placed right here at this position, that is also the time for the first, second, third signal. That's a 2-second time delay. So at a 2-second time delay from the second signal emission, this person would actually get the signal right here if they were positioned right here. See how simple this is? It's easy to track everything. You can't wave your hand and use magic formulas to do different things. You can actually just do geometry and time and calculation and physics. So I said, well then, what if V equals C? Well, you'll notice that this is the same similar situation that I used his diagram and extrapolated from it. You could come up with geometry and formulas to relate all these things that you see up here, time times velocity, giving you a distance, where the observer is versus this. And you can notice that if you start going into an eternal time, the longer time evolves, these circles grow and grow and grow and hit these positions here where you'll never actually see, in this area right here, you'll never see the signal, the second signal, depending on where you are. If you're out in here, you won't see any of the signals. Now this is at V equals 2c. I'm just expanding the circles at the velocity of the speed of light as the source is being the center of that circle or that emission point and continuing with the constant velocity. Extending it, I'm taking his research and going to the next step. For example, if I would have been a disciple of his trying to not get a PhD from him, but to just actually extend his work. And
Okay.
he appreciated that.
Now, in what you showed up to the first slide that referenced the extinction principle, that's your work, or is that Dowdy's?
That's my work. That
Okay, because in your example, the line PQ
yes, sir.
separates the sources of the two signals, right?
Yes, sir.
Okay. Now, when I saw the Lorentzian clock retardation, they had a triangle, but PQ was for separated two different observers.
Correct. They were two separate sources in two different locations at fixed. They were like lights on a light pole stuck to the ground or something.
Yeah.
Or fixed locations in space.
So you may be refuting that particular example, the light clock example, but there is, if you hold that when the light is emitted from the source, it instantly goes at speed c in a single preferred frame. Then you do get a Pythagorean theorem, but the PQ line is really for the recipient, not for the source. So you don't have the problems that you talked about in your example. I'd have to look at the light, that particular example that you talked about for light clock. Maybe there the source is moved.
Okay, so from what I understand, Dowdy would say, and if you look at his diagrams, that from P to Q, light does not move at C, it moves at V plus C. That's what his, and his paper, I can send everybody the link to his paper. I
That'd
can
be
do that
good.
right now.
So
Yeah.
just on that, did you say, and I think Dowdy says it, that you have to add or subtract the V from the C when the source is moving. So in other words, you're saying that the speed of light isn't independent of the speed of the source.
Yeah, unfortunately,
Correct.
that's
Very
not
correct.
correct, because
That's not correct. Yes, that's my view as well.
because the data from binary stars shows that that's
Yeah.
not correct. It's source independent. So
Yeah.
So if you're saying that, Harvey, and if Dowdy is saying it, well, anyway, we would maintain that the experimental evidence is against that.
Yeah, but the thing is the plasma universe concept says that binary star systems are basically the anodes of a larger electrical circuit that connects the stars to through Birkeland currents themselves to other solar systems and other stars, and you get hence the cosmic web. And so that plasma, one thing I'm just giving you an introduction to his theory. His paper that I'm getting ready to, where's the chat? Because that would be interesting. Where's the chat? I'm sorry. Okay, I found chat and I've opened that up. And now here's his paper where you can actually see what he says. So if you take his paper and download it right now, you can literally see what I'm referring to. And what he's saying is, let me see, I have a copy of his paper too. And I'm opening up the same paper on my screen.
Sorry, Henry and Ed, I just wasn't sure.
What he's saying
is this the son of Ed Dowdy? Sorry to interrupt you. You said Henry Dowdy.
that's his middle name.
Oh, okay.
Well, it's
Same
Dr.
guy.
Edward Henry Dowdy Jr.
Okay.
Sorry, that's my bad. Did I get his name wrong?
Well, I think you said Henry Dowdy in one of the slides, but
Yeah.
we normally say Ed Dowdy.
Yes, yeah, it's Ed Dowdy Jr. There you go. That probably answers your question right
Yeah, it
there.
confused me
Sorry.
when I saw JR.
My apologies. So he talks about moving windows. And so the thing is you'll have an observer make an observation. So see, here's the thing. If you believe that things are limited by the speed of light, then the wavelength can only be limited by the speed of light over that distance. But if it's going twice the speed of light, for example, muons we know only last 2.2 microseconds. So if you pick your poison, 15 kilometers, 10 kilometers, it doesn't matter, 30 kilometers, how can they make it to the Earth? Well, what if the cosmic rays themselves are going 22 times faster than the speed of light because of the cosmological event at the beginning? The energy that was flowing was moving much faster than the speed of light. And we have this afterglow effect of it. But we are limiting our science thinking. It can only go at C. But he says, if you look at his diagram, which I'm going to find, he talks about moving windows on page 4. Or there's a window on page 4, figure 2.
But Harvey, let me interrupt and say that you know, the muons reaching the Earth can be explained by atomic processes, like atomic clocks, are slowed when they move at absolute velocity with respect to the ECI frame, at least in the vicinity of the Earth.
But what changes its clock? You can't take a clock and I can't grab the fingers of a clock and move them and make them go slower for someone. You see, the time.
Right. We don't know
everything.
exactly, but the empirical data seems to be pretty conclusive that atomic clocks slow as a function of their absolute velocity with respect to the ECI frame. Now, I happen to think it's absolute velocity with respect to the Earth's gravitational field, or whatever the prominent local gravitational field is. And haven't worked out the details, but.
Has anybody ever done this though? Like I've seen experiments like at Super Keiakumande, like 200 kilometers away in Japan, they have a linear accelerator. So it's accelerating high energy muons or particles, high energy particles towards their detector that actually gives them light signals, right? And so they know those signals came directly from that detector, because these are all underground and they're huge. Has anybody ever actually said, let's just synchronize clocks and have 2 GPS clocks in 2 different locations, do this high energy experiment, or measure muon spray coming in and the time difference of this spray from one location to another location, and then calculate it without using relativity? Just say, what is the distance and what is the time difference that we see on the 2 clocks? And we know that if the clock, what's the accuracy of a clock? I think it's in the femtoseconds, isn't it? What's the accuracy of it's like in relativity, we only have a 5 or 10 or 15 second, whatever that delta is, it's femtoseconds, I think it is, in a whole year, how they drift from each other. So we ought to be able to do an experiment that only takes a couple of microseconds to do. You know, you just pop the things on, turn them on, flip the switch, take the measurements, and let's just say, forget relativity. What was the time here, and what was the time here, and what was the distance? And they'll say, oh, the lifetime of the device slowed down so that it could actually go longer and exist longer than we projected. But you have to invoke relativity. And I'm saying, maybe that's not, maybe, you see, that's my thinking.
Well, one thing that might contradict that, you know, accent of the distance, is that at CERN, the most accurate model for particle decay is using velocity with respect to the ECI frame. And that's a very high energy environment. So it's all explained by Lorentzian theory locally. So we don't have to, maybe there's some other thing in addition, but that data can be explained just locally, and it's consistent with the GPS data. My contact at CERN is John Field, not necessarily the author of field theory, but he's the expert on particle delay times. That data.
I saw a video, and I wanted to do this before our meeting, but I just didn't get time. I was more focused on getting my presentation ready. And that was where the guy who has the CERN on his shirt, and he's actually presenting on relativity stuff. And he shows the time dilation where you have to do some kind of, he says people misunderstand it, which I'm one of them probably. But he says you still have to invoke time dilation on those experiments, because he set a muon 2.2 microsecond lifetime. He says it, no matter what you say, it has to be that lifetime. That's all they live. And he said that means in this particular experiment that he did, it would only travel about 1 meter. That's what he said. I thought 1 meter. Maybe it was 20 meters or something, but it wasn't very far, which was in their observation space. But he said they had to actually go further out, and they can actually measure the decay of the muon a quarter mile away. So he does this little walking, with the, accelerated time. It's pretty funny. I like it. I'm not making fun of the video. I think it's cool. He says, I have to be all the way over here to actually do my experiment to detect the decay. But he uses relativity to do that. And I would just say, why doesn't he simply just have a clock at the point of emission, whenever the collision happens, have something that measures that collision, doesn't care a hoot about what goes on beyond it, have another detector with an atomic clock at the reception of the event, just let the two go. And then whenever, make the clock stop or have a tick point somewhere in that's, counting its counter. I've seen atomic clocks before, and I've seen them count, and actually have it, or at least on video or something, where you take the difference in the femtoseconds or whatever it is between the two and the distance and say, was it faster than the speed of light?
Well,
that would be direct disproof.
Yeah, it's a little bit difficult to identify muon 1378 at collision point and at the, say, the surface of the Earth. You don't know. It's hard to differentiate one muon from another. But if you just apply the Lorentz clock retardation factor in terms of velocity with respect to the ECI frame, it correlates very well with the data. You don't do it on individual photons. What you do it is it's a statistical average. It's a little bit different than an accelerator where you are looking at, you have the beginning and end time for the lifeguard. On the lifetime as a path that you have right in front of you. But
so
there's no problem with using normal clock retardation, atomic clock retardation, or atomic process retardation.
But if someone was to just say, let's have a detector, well, okay, when the event happens, because you get all this spray coming from the event, right? So you're not,
but you don't know that in the upper atmosphere.
No, I'm talking about from from the CERN. Let's just say the CERN has an event, and then downstream from the CERN, they know they're going to detect that event. So they put some kind of detector down there, whether, all in a vacuum. And we're not caring about which photon goes, which particle goes where. Like maybe there's a billion particles and you're detecting a few at the source of the event. So it has a little tick mark and it says time 10000111111, bam, you know, that particular time in femtoseconds. Then the other detector says, wow, I get this big disturbance at this delta time later, a huge spray of stuff, and it just stops its counting at a certain position, point. I mean, it's going to keep counting, but I mean, its digital counter stops and it records what that instant was, because the distance between its measuring devices and itself is so much shorter than the quarter mile we're talking about. It's maybe only maybe 1 meter or a couple of centimeters. Okay, so then you just take the two clocks and somebody just simply reads the numbers. What are the numbers on the two clocks? Because they were pretty well synchronized before the event. They were within 1 or 2 numbers of each other. And then lo and behold, when one stops and the other one stops, and the distance between the two would say, you must have had a velocity that was 80 times the speed of light or 20 times the speed of light or something. And you don't have to invoke time dilation or any of that stuff. You just say, that's exactly what happened. Something went from here to there with a certain velocity, which we're going to calculate simply using Newton or Galilean or Newton velocity formulas. And then you see what I mean? That's all I'm saying.
Right.
If I may just make a point
Can we do that
a
experiment?
bit earlier, with respect, I think that the invocation of things like muon decay and atomic clock behavior, you know, to sort of whether relativistic or Lorentzian type processes, has blinded us to investigating in more detail what perhaps are the physical causes of such changes. I believe they're effectively physical, and you know, maybe there are coincidental reasons why the formulae are similar, but I don't think we have to invoke that, and I think we should really look for the physical causes of these rather than, you know, start trying to reanalyze what is basically a sort of a relativistic effect and, you know, put it into an earlier form. I mean, at least Lorentz to a certain extent did that, because he talks about the behavior of electrons and electrostatic fields as they move. So you know, he wasn't divorced totally from the physical effects. But I think we you know, we're sort of questioning the special relativistic analysis, but we actually have the legacy of that way of thinking in our minds. And with respect, I think to a certain extent, maybe I would differ from a lot of what has been said, you know, but by you and somewhat by Nick as well, you know, in trying to amalgamate the things together when I think they're actually disparate.
Well, we definitely need to focus on, you know, what's the physics, the detailed physics that causes this slowing. And people have been trying to do that, but it's not that easy. As I say, I've come up with one suggestion that it's interaction with the gravitational field, whatever that is, because at least there's a correlation in the data between velocity and also with kinetic energy, and also clock rates with respect to the gravitational potential. So that led me to think it was interaction with the gravitational field. But let's see. I think the fact that with an accelerator, we know the speed that's going, because we have a record in ink, or whatever the magnetic, however it's recorded, we can see the path of the particle from inception to its end. So it's pretty in effect, we have done that experiment already.
Well, I guess the issue might be, so you're saying inside a collider, and I've seen some work on it, but I just haven't delved deep into it. It is known that the particles really are traveling only the distances that the circumference allows them, you know, of the circuit itself. and they are making as many passes as we think they should be making in over a period of time as we keep pumping more energy in it. And once they get like 0.998 C or so, we say we got enough energy in there. Let's do our experiment. We divert those particles to a target, right?
Yep.
Okay, so then what if mass times velocity input is equal to mass times velocity output? That's the thing. So that if you had particles going with a certain momentum, input could literally have other smaller type particles that are maybe transitory exiting at greater than the velocity of the speed of light. And we invoke the Lorentz transformations to explain the results. That's all I'm saying. When it's not necessary. That's just an idea of mine. But one thing I did, you mentioned gravity, and one thing that I did was I took the path of the source from time t=0 to time 3 seconds or whatever. And if you draw that angle and you fill in that triangle to where the observer is, so you'll get like an obtuse or an acute triangle, you'll get a triangle that, you know, is, I think it's called obtuse, correct? Where the angle is greater than 90 degrees. That area divided by the time of transition is a constant, even for the future of that particle. I found that out. It's like Newton's, like Kepler's law. You know, on Kepler's law of planetary motion,
Yeah.
the area swept out from the
Yeah.
focus of point is a constant regardless of where you are, but the velocity is changing there. So what I would like to do, and I'm still, I do have, if you would like in the future, I have a paper that I haven't published. I put on there, draft, where I actually do the time, the length contraction. And I show that there is a hyperbola that the observer can be at a constant, where the sources are at a constant, where these ends of the rod are the moving sources. So as a rod is going through space, it emits two signals simultaneously at when the center of the rod, or no, where the end of the rod, the trailing end of the rod equals time t. Well, I can't remember exactly the details, but the point is that if you're at the right location and you're an observer, you will get both flashes at the same time.